We will take an example for the concepts that we have just seen, specifically going through an example of adaptive segmentation and modeling. So the type of physiological signal we will look into is the knee sounds, also known as WAG or vibroarthrograph. We have come across many other physiological signals, and we have seen its implementation either in the lab or also through your project. So this one is a pretty unique signal in the sense the characteristics of this signal is highly dynamic and non-stationary. So the following is a data acquisition block diagram in gathering knee signals. Why would somebody analyze a knee signal? It's essentially to understand whether the knee is prone to be arthritic, to be specific, osteoarthritic, or normal. This arthritis need not be for elderly people. It could also be for young adults, especially if someone has gone through sport injury. It's highly likely somebody could develop arthritis in the near future. So it becomes quite important to find out a method of non-invasively understanding the knee conditions so that we could avoid the repeated process of arthroscopy. Arthroscopy is a semi-invasive procedure where a probe is put into the knee joint and the cartilage surfaces are being observed by the orthopedic surgeon. Non-invasive methods include CT and MRI, but the difficulty in getting appointments and for repeated diagnosis and monitoring, it may not be appropriate. So a signal processing approach like the one proposed here might be a good alternate solution. The system is very simple. It uses an accelerometer as a sensor on the knee cap or the patella. And we ask the subject to move the knee joint at an angle of almost like 135 degree back to 0 degree and 135 degree. So this swing happens normally in a time duration of 4 seconds. The reason to put the knee in some kind of a swing motion in this 4 seconds is to create articulation between the knee joints, especially the patella, the tibia, and the femur, so that vibrations would be produced, which could be recorded using the accelerometer. Okay. So it has to be recorded in a dynamical condition. And the role of the goniometer is to basically provide the angle label information, like what was the angle of movement of the knee joint. So the VAC signal goes through classical biomedical instrumentation before it's stored in the computer. Okay, so classical way. So in this specific project, the knee signals were sampled at 4.5 kilohertz. In other words, 2,500 samples per second, and 16 bits per sample. Okay, so the quantization was 16 bits per sample. Okay. The database that I'm talking has been collected in University of Calgary in Foothills Hospital, where essentially many subjects have gone through ski accidents and their acoustic or vibration signals from the knee were recorded. So the word sound acoustics vibrations are interchangeably used. They all mean it's a VAC signal. So this is how a VAC signal looks like after going through the process of an adaptive segmentation. The main reason to do adaptive segmentation is basically to overcome the difficulties or approximate aspects associated with fixed segmentation if adaptive segmentation isn't used. So this signal in the x-axis, it's 4-second duration. Given the sampling frequency was 2.5 kilohertz, so you have 10,000 samples. So if you would have used a fixed window, let's say 128 samples, then you might be needing around 100 of those, approximately 100 of those windows to do a fixed segmentation of it. And in many cases, it doesn't capture the dynamic characteristics of it. Whereas by using an adaptive segment, these are the boundaries that the dotted lines denote the various boundaries obtained through the adaptive segmentation process, which might be as simple as tracking the learning curve or the error squared curve in a least mean squares algorithm, LMS algorithm. So what you see is two examples of the knee signals obtained from a subject who has a normal knee and a subject who has an abnormal knee condition. So the segmentation has given what we call quasi-stationary, in other words, stationary segments. So this, the whole signal is a non-stationary signal because knee signals are very dynamical and complex. So the behavior is non-stationary, and unlike other signals, there is no defined morphology, like we don't have something like a QRS pulse here. Only obvious thing we have is something like these transients, which are like the knee clicks, okay, the click sounds. The challenge comes because even a normal knee gives a click sound. Now, how do we kind of distinguish that from an abnormal click? Okay, so the segments, once we have quasi-stationary segments, then we could proceed with the subsequent processing of it, such as modeling. We could also use the fixed segment and went with quasi-stationarity assumption, but it would have probably done over segmentation and probably would have also split the events of interest. Like probably it might have got a particular knee event, like the grinding sound. So this is an example of where there was some kind of a grinding sound could have been further segmented, and the information of interest would have been approximated and lost. Okay, so this is a good example of where adaptive segment comes in pretty useful. And the labels you see here, 0001, they're all coming from the inference of the orthopedic surgeon who got to listen to the knee sounds and basically coded the different knee adaptive segments, either whether it's quiet or was any kind of noise was heard. For example, when it was coded as 1 and 1, it means when the knee was being moved 135 degree to 0 back to 135 degree, the orthopedic surgeon did listen some sounds. Okay, in other cases where it's 0, the surgeon didn't listen to any noticeable audio events or clicks or sounds. Okay, so that's kind of the label information. So the labeling has come from a couple of orthopedic surgeons who were involved in the project. So the domain experts have provided the labeling for each of the stationary segments that is within the knee signal. So now we have a signal which is adaptively segmented and labeled. The next couple of steps are essentially to go with feature extraction and machine learning. So the feature extraction that could be used to start with is the autoregressive model coefficients that we just discussed. And as you know, this is an all-pole model, and these coefficients A's are the autoregressive coefficient, and we have M of those. Okay, so there are M autoregressive coefficients, A up to M. For each of the knee segment or adaptive segment, because they're quasi-stationary, you could apply this model H of Z only in those stationary segments. Then we extract these parameters A to AM, which are nothing but filter coefficients coming through the process of linear prediction that we just saw, but it's connected to also autoregressive coefficients. So A1 up to AM is one set of features. Now, definitely the denominator in equation 1 could be factorized into poles. So we also have M poles in the system, P1 to PM. The good thing about the poles when as compared to autoregressive model coefficients, though both convey the same information, the poles could be plotted in the pole zero diagram. So what you are seeing here is a pole diagram, because we don't have zeros in the system. It's just an all pole diagram. Only the first half of the unit circle is shown. So the first half goes from 0 to fs by 2, which is nothing but 1250 hertz, because the sampling frequency in this application is 2.5 kilohertz. So this has given a nice visual representation of the pole diagram for the normal signal that we just saw, and also for the abnormal signal we saw. Okay, so the poles are now visualized, which are features. So rather than using the entire segment information X and using other feature extraction techniques, the feature we are taking here is poles. You could go one step further. You could basically ignore some of the poles which are far away from the unit circle, because they don't really contribute to the peaks, the spectral peaks. In any signal processing application, the feature are quite prominent when your spectral peaks, and spectral peaks comes when the poles are closer to the unit circle. And it goes back to the first module that we learned. When the poles are closer to the unit circle, the distance between the unit circle and the pole is very small, and that basically makes your magnitude response quite high. Okay, which is the reverse of when zeros are there. Okay, so poles closer to the unit circle will create spectral peaks, very sharp peaks. So if we could go one step further from this pole diagram, we could pick the poles which are very close to the unit circle, like pole like this, this, and few other, like maybe 5 or 6 of these poles, and we can call them a dominant pole. So we can do a further reduction of the m poles to a subset of poles if we want, okay, depending on how many numbers we want to select. Nevertheless, now we have extracted autoregressive model coefficient A's and P poles. The third feature that could be extracted is a simple and nonlinear feature, nothing much to do, just taking log on that transfer function that we just saw. So this is a transfer function of the model, which is nothing but connected to coefficients and the poles. Now, if I do the log on this thing, then by using the Lorentz series from mathematics, Lorentz series, the log of a complex number could be represented by this expansion. And going through the steps of this, I'm just substituting h of z there, going through the steps of it and trying to equate the values, it ends up that we could find a relationship between this expansion coefficient C and the autoregressive coefficients A. Now, C's are called the Kepstrel coefficients, essentially they're derived from your AR coefficients, but through a logarithmic process, okay? So it's very important here because it allows to do some kind of a simple nonlinear transformation. Log, by the way, is a simple nonlinear function. It does a mapping in a nonlinear way. So by doing the log on the AR model, we have obtained another set of coefficients called Kepstrel coefficients, and they are linked. So C1 is nothing but negative A1. The other C coefficient, other Kepstrel coefficients are linked through this expression, simple mathematical regression expression, which is just provided there. So you see here, I mean, from AR coefficients, we could do some simple nonlinear transformation as per equation 6 and obtain my C coefficient. So now I will have C1 all the way up to Cm, because I have M coefficients, just like AR, we have M coefficients here also. So now this is another feature. So you got the point. From the same adaptive segment of an E signal, we have obtained 3 different sets of features. And we know from the theory, which relates to the physiological process, we got an equivalent of that. Poles are great because we can visualize that. We can see that in the unit circle in the Z plane. And now by just using a log on the AR coefficients transfer function, we got what's called Kepstrel coefficients. So this is the third feature that we got. Now we can follow any machine learning framework. So here we are using the idea of logistic regression here, and in this logistic regression formula, it's just finding whether the event has occurred or not. Essentially, this is the function that's been fed into equation 8, and all the x1, x2, all the up to xp. By the way, it represents features. It could be m, but p also means that maybe I'm doing some feature selection from m features that we just talked. I'm selecting p significant features, okay? But normally m and p are the same number. But if you take a subset of m, you could call them p features, just like how in poles we talked about extracting dominant poles, especially we know the poles closer to unit circle are significant. So similar to that, when you extract a subset of the feature, which is called feature selection process, then we have p of these features, okay? So here the features are nothing but x1, x2, all the way xp. So your x could be either AR, or x could be either poles, or x could be either Kepstrom. So you have three different feature models that you can feed into that, okay? Sometimes you can combine them, but it's not recommended because one feature is basically derived from the other. Combining them is an additional layer of redundancy in the system, okay? Now, as you know, the logistic regression from the machine learning framework, all it does, it estimates the B parameters. In other words, it gives a weightage to the features. Dominant features will get more weightage, and that weightage, the coefficients B's are determined in an automatic way by using either the least squares approach or the maximum likelihood method, okay? So yes, we have designed some form of an ML here. Now, in terms of the results we got with WAG by using those features on the logistic regression classification accuracy, by using AR features, your A coefficients, for the two group classification, normal, near, abnormally, we got 74% accuracy. By using the dominant pole features, P poles, we got 78% accuracy. Just by using a simple nonlinear transformation of those coefficients, we got Kepstrom coefficient C, and it gave an accuracy rate of 84%. So what it's telling is that good feature extraction with the same machine learning, because the machine learning approach in all these three cases are the same approach, has allowed us to get a better result. And that slightly better result of 84% is coming because of the simple non-linearity we introduced in the system. This also gives an idea that in a complex process, like where we are analyzing knee sounds, which are not as characteristics and as structured as other kind of physiological signal, the signals are non-stationary, and there is also some kind of a non-linearity inbuilt in the system. We can work most of the things with the linear features like AR features and non-linear features. Kepstrom, by just doing a simple log, has allowed us to get better results. The same thing applies because the concept that I just discussed, it's been known in the world of speech, which is also an acoustics and audio type signal. In speech world, the most dominant feature over the many years of research and innovation has been determined to be MFCC, which is a Kepstrom coefficient. CC is but it's called Mel frequency Kepstrom coefficient. So in other words, it uses the Mel scale for shaping the Kepstrom coefficients, and that's kind of the most powerful feature for audio and speech analysis, specifically for speech and also for other audio signals, okay? So if you take any machine learning outcomes of speech-based work, you would see MFCC as a feature that they would have used there, okay? So same thing has reflected here because knee is some kind of an acoustic sound signal, though it's not as structured as speech, and it has shown prominent results, okay? So this gives an idea on the problem. It's a real world problem, has been handled, and the same thing could be used for other physiological signal, whichever signal you're using. You can go through the same process by using simple machine learning techniques like logistic regression. You can get good accuracy rates. If you use LDA, you will get the similar results, and so forth. It's all supervised learning because we did get the labeled information from the orthopedic surgeons who were collaborating on this project. So now we have got a totally non-invasive machine learning system which is almost 85% accurate in determining whether your knee is normal or abnormal. So more than diagnosis of this condition, when somebody is going through therapy, when the knee is abnormal, they're going through therapy, this gives an idea, okay, whether the features are migrating from the abnormal zone to the normal zone. And for the visualization of the features among the three dominant poles are good. Having said that thing, now there are many visualization tools. You can also visualize other features, but you may not be able to have this direct connection to something like a Z-plane and a unit circle. They are all foundational and fundamental visualization things, whereas the other visualization I'm talking is just looking into the cluster map of the features, which are all just additional tools added on top of that. Okay, but this is just a simple example. This could be expanded to any other area of physiological signal segmentation, followed by modeling and ML approaches.